which is a topic I think a lot of us feel we've seen. We all know the standard graph, a bunch of dots that are moving in a line, and you can fit a line to it. Something I've discovered in this community is that a lot of people seem to treat basically everything in sklearn kind of as a black box. And what I want to do in this talk is open up the black box in the simplest case possible and just show how if you can open the black box, you understand how it works. If it doesn't quite work for your application, there's a very good chance you can probably just alter it slightly in order to get good results. So I'm just going to illustrate a few examples where I've used linear regression, or someone I know has done so, to make money, typically by gambling. So around this time last year, I was making not a lot of money, but at least some money, gambling on, I wasn't actually doing cricket, I was doing baseball because I was in the US at the time, but similar idea. I had data that was along these lines. We have a batsman, we have a bowler. In a certain game, this pairing of a batsman against a bowler resulted in this many points. So Major League Baseball is actually very nice because they have an XML API where you can get all the data you want. So what I did is I set up a linear model using one-hot encoding where basically I have each batsman has a skill, which is BI. The bowler or the pitcher has a skill, which is PJ. And so in the pairing against those, we would expect to get this many points. This notation is worth noting. SIJK is the score of batsman I against bowler J in game K. And G is a probability distribution, which I'm not going to specify right now. So you could think of it as, in some sense, as being a Gaussian centered at mean constant term plus batsman skill plus bowler skill. But what I'm going to get to later is that it doesn't have to be a Gaussian. So we make some important assumptions that the game performance actually behaves linearly. We also assume that the score in one game doesn't affect the other, which are mostly reasonable assumptions. But nevertheless, I was making money in this case, and I was beating the average gambler, even though most of the standard assumptions of ordinary least squares, which we're all familiar with, didn't apply. Here's another example that a friend of mine is working on. He wants to price heavy equipment. So he's got a backhoe or some other piece of heavy machinery. He knows how many hours it's been working, how old it is, whether it's got an air conditioner, what's its horsepower, whether it's got four-wheel drive, and he wants to know what this thing will sell for. Because what he's doing is he's building a pricing model to help lenders accurately lend money, and this is collateral for the loan. So an accurate price is valuable. And in this model, we again set up the same framework. We say the value of a machine is some constant. We add in the value of, or in this case, subtract some amount of money based on how many hours it's spent working. Something else, whatever the value of four-wheel drive is. And this generates a reasonably accurate prediction of what a machine might be worth. Some years back, I was running a model in the stock market. I had a little Python script that ran a couple of times a day. It would submit trades on my behalf. And in that case, I was essentially using the prices of fast-moving stocks, such as Google or Goldman Sachs, to predict much slower-moving stocks, such as JNUG, a little bit later. I wasn't actually trading JNUG. That's just a Wall Street Bets joke. But I was trading similar shady stocks on the basis of the movements of faster stocks. And so again, the model was, in some sense, linear regression. I predicted that the price of the slow stock at, let's say, 10 milliseconds later, I wasn't actually doing it on the millisecond scale with a Python script, would be drawn from some probability distribution. So the delta means the change in stock price movement. So if Google went up, JNUG will also go up. That would also be drawn from, again, some probability distribution, which is linearly derived from the input variables, namely the fast-moving stocks in this case. This strategy is now tapped out, so if you want to know more details, I'll be happy to tell you them, but it's not going to make money anymore. It stopped making money a couple of years ago. So we're making an assumption that whenever we do linear regression, or more or less any parametric statistics method, we're sort of assuming that the world we live in some sense, a simulation. And moreover, we know specifically what is being simulated. We have an idea of the code. And the code is typically, in the linear regression case, we draw a variable z, which is a dot product between some unknown vector a and x, which is our observable input data. And then we take g. So g is the probability distribution of the exact, choose any of your favorite probability distribution classes from scipy.stats, normal distribution, exponential distribution, whatever. And you build that distribution, you set the mean and the scale parameters equal to some linear function, and you draw a random variable from it, which is what the RVS is. And then we assume our data is generated in this way. So just for the sake of notation and to move us forward, I'm going to always call x the input and y will be the output. So if you ever see x and y on the slides, I should be consistent with them. And so our goal is, assuming we knew the probability distribution that the simulation chooses, we can find A and then use A to predict Y. So this is, by the way, called a generalized linear model. It's a different thing from a general linear model. You can look on Wikipedia for the distinction. It's very confusing terminology. So I want to distinguish between data science and statistics here. But this is an important distinction. Statistician says that we live in a simulation, the matrix of some sort, and we say the machines are running this program. Not just any program, but this particular one, and we know the code. The only thing we don't know is the config file, which is the value of true A. So what a statistician does is he will then essentially attempt to look at the output data and try to figure out what the config parameters are, what true A is. Data scientist takes a very different, more computational perspective. He doesn't assume he knows the specific code the machines are running, and instead just sort of chooses from a largish space of computer programs. He searches through this much larger space to find some totally different program that bears no relationship to the code that the machines, our simulation overlords, wrote. And what he instead does is he just tries to write a similar program, a clean room implementation that looks nothing like the original, but generates the same output. So I'm going to be talking about statistics in this talk, and I'm mostly going to be leaving machine learning aside. I'm not sure there's consensus on this distinction, but this is the distinction that I make that makes the most sense to me. So don't consider this to be anything that everyone is going to agree with. So I'm going to discuss this talk from the perspective of Bayesian statistics. So in Bayesian statistics, we try to form opinions about the world. We represent our opinions as math. Specifically, an opinion is a probability distribution. So I've just reminded everyone here what a probability distribution means. It's a function that takes, the input to the function is your true parameters. How much a four-wheel drive is worth if you're in backhoes, how much JNUG is going to move if Google moves if you're looking at stock prices. Those parameters that you're having difficulty finding. So our function P of A, it has to be positive. It has to integrate out to 1. And where this function is larger, that means we have a stronger opinion that that value of A is likely to be the true one. So in Bayesian statistics, we're strictly saying that probabilities are opinions. And Bayesian statistics is about changing your opinion, but it can't give you one, you can't create an opinion out of nothing. So what you do is you start with an opinion, just anything you believe before you see any data. This is called pulling a prior out of your posterior. then you can use Bayes' rule once you have data to change your opinion. And this will change in a way that is mathematically optimal to something that is more accurate. So essentially what happens is the function p, probability of data given A, means assuming A was known and this value, what is the probability of seeing the data we just saw? We're multiplying by that, which means that if the data is highly inconsistent with the parameter we just saw, that will have a low value. So if the data and your theory disagree, that's going to be small. And if the data and your theory agree completely, that will be large. So it's basically making your opinion smaller where it's inconsistent with reality and larger where it is consistent. So let's discuss linear regression from this perspective. We are saying that given our outputs, y is the output, x is the input, and a is the parameter that is unknown. So a is going to be the slope of the line and the constant. We can compute the given our assumption of independence, and that's the price of one backhoe doesn't affect the price of a different one, the score in one game doesn't affect the score in a different game. We can essentially write the likelihood, probability of data given our parameter, as a product. And it's a product of the density function of the distributions we're sort of assuming govern the world. So with this formula, we can what the rest of this talk is going to be about is different ways you can take this formula, plug it into Bayes' rule, and get better results even when all the assumptions of least squares don't apply. So the simplest example we'll start with is we assume G is a normal distribution. And that's just a Gaussian, which we all know and are familiar with, and we're normally told that linear regression requires a Gaussian, requires Gaussian errors. So the other important fact, and I'll flip back to the previous slide, is that term at the bottom, probability of data. That term doesn't vary with A. So it's going to be kind of lucky that it turns out this way because I'm going to get to ignore it. That term is very complicated to compute, but I'm going to get to ignore it for the rest of this talk. And you'll see why shortly. So here is the heart of Bayesian linear regression. We write down our prior, which is something we're going to have to choose based on our opinion about the world and what we think is reasonable. Then we write down the distribution probability of A given data, which is a constant times our likelihood. And as we said on the previous slide, that's just a product of the individual probability distributions times our prior. And then step 3, there's different ways to set this up, but it's basically let the computer do a bunch of work. And when I say a bunch of work, it can be quadratic amounts of work in your error. So this is not a specific algorithm, but it's a framework for coming up with other ones. And you'll see that from this framework, we get a lot of the things you've probably seen before. So, first way to let the computer do a massive amount of work is Markov chain Monte Carlo. What MCMC is an algorithm, as an input it takes a function. This function should be proportional to a probability distribution, but it doesn't have to be the actual probability distribution. I'm not going to say how it does it, but what this function does, very slowly, is it outputs samples from the probability distribution. So this is, you can get this from the PyMC library. The convergence rate is O of n squared, which just comes from the central limit theorem. And if you can avoid doing this, your computer will thank you. But if you, in the absolute worst case, you can always just run this and eventually get a result if you're willing to throw computer power at it. So just to really emphasize, it can be hours versus seconds if you can do something more clever than this. But it's still a good place to start. So, as I said, you don't need to know that denominator, which is hard to compute anyway. So, in 2008, a guy working on Wall Street told me that about 70–80%, I forget the exact number, but it meant a very large fraction of computing power in the world is computing MCMC. This is because it is even though it's slow, it's a brutal workhorse that will get you the answer. And if you're trading bonds, you really have enough money to throw at MCMC if it gets you the right result and lets you make a correct trade. Nowadays, it might be SGD, given that deep learning is now a big thing. So here's the implementation of PyMC. We essentially set up our equation. So we have this deterministic function, linear regression. We apply a Python decorator to it. And prior to that, we specify the distributions our parameters come from. So A and C are the constant terms in linear regression. And the value x is our data. So as you can see, we say value equals x data. What that means is whatever the input to regression is, whatever the data we're trying to fit is, this variable is specified there. And similarly for y, so you see the value equals y data parameter, that's where we say this is known, we ran an experiment, this is our input data, whereas A and C are parameters that we don't know and we're trying to find. So then we run the model, and essentially just by setting up the model this way, we can get results. So the output is not a single answer, but a sequence of answers. So this trace function outputs a set of A's and a sequence of A's and a sequence of C's that all represent values that are plausible given the data. So this graph here, the dots are the actual true data. And what the red lines are, so can everyone see that that's a large number of red lines, or does it look like just a blur in the back? So where the red came from is for every value of A and C, I plotted a red line. So what we're getting out of this is a sequence of plausible regression lines, together with what is essentially an estimate of the uncertainty in our beliefs. So we're forming an opinion. And just because we have one best fit line doesn't mean that other nearby lines are just impossible. It actually means that quite a few of them are plausible. And one very good reason for doing this is, even though it's much more computationally intensive, is let's say we had fewer data points. There's more lines that can plausibly fit 10 data points than can fit 100. So as you can see, if we compare it to this, we have a pretty narrow band, especially in the middle. The red lines are pretty sharp. There's not too much width. And when we go down to 10 data points, our estimates are a lot fatter. We have a lot more uncertainty. And this is kind of what you expect. Less data, more uncertainty. So if you use MCMC and you use the full probability distribution, you actually get a good estimate of this uncertainty, which doesn't come out if you just use a method that gives you a single point estimate. Another way to sort of brute force this, which is a lot faster than MCMC, but gives up that uncertainty, is something called max a posteriori. So what this says is we take the prior and we take the likelihood. Essentially, we take that probability distribution that comes from Bayes' rule. And what we do is we find the value of A, which makes that as large as possible. So this is much faster. You can do gradient descent usually or something similar. And it'll give you a single best estimate, but it won't necessarily give you an estimate of the uncertainty. And as a computational trick, we usually take the log because the actual functions will be very sharp, whereas the log will be much smoother, and so all your optimization algorithms will actually work. And in code, we're essentially doing this. We define our prior. We can define a log likelihood. So that K is just training versus test. And then we can compute a result using the SciPy minimize function. So ignoring some tricks that are in linear regression, this is basically what sklearn.linearmodel is actually doing. It's doing some kind of optimization. And they use tricks to make it faster. It's a carefully optimized module, but this is a big idea. They've defined a likelihood, they've defined a prior, and they're optimizing A. So at the end, you get an optimization result. Hopefully the message will be optimization terminated successfully. Didn't happen every single time when I was preparing for this talk, so I had to tweak a few of these things to actually work. And then you can read off the result of regression from the X parameter. So let's let's talk about ordinary least squares, which is the standard thing I think everyone in this room knows about. So what ordinary least squares does is it takes Bayes' rule and it ignores the P of A term. It ignores the prior. So it's not technically correct from a Bayesian perspective, but the frequentists say that's okay, we want an objective, unbiased estimate. So here's a simple version. We're going to let our function g be a normal distribution. So we're assuming the data was drawn where, in that previous slide where I said I had a function g, it just imports scipy.stats, norm of these parameters. This is our function g, and this is the data set generated that way. Now, what I've done here is the stupidest way of optimization possible, namely a grid search. So I'm not even doing gradient descent right now. I'm computing the likelihood as a function of the data. And as you can see, this exponential is literally just the likelihood. Actually, this code is wrong. There should be multiplication. That should be times equals. But if that were times equals, then this plot would be about right. And so what you can see in this data, which on the previous slide I generated with the true A being 3, this likelihood has a peak in the general vicinity of 3. It's not exact, but it's close. The other thing that comes out, so you could find that with grid search, and you could use gradient descent, but in one dimension, who cares? You can also just look at the graph and see the result. Obviously, that doesn't work in practice, but in examples, it works. And then the other thing that comes out is when you change the sample size, this distribution becomes either fatter or narrower, which is, again, what you expect. But if you're only looking at the top, if you're just taking that one best estimate and not looking at the width, you're essentially throwing this information away. So this is ordinary least squares. I've done nothing Bayesian here. And so what we can do now is let's look at it from that perspective, nevertheless. If we take the probability of the data given A, so we've ignored the P of A term, we get, if we do a little bit of algebra, we get the exponential of the sum of the squares. If we take the log of both sides, we just get the sum of the squared errors. And essentially what least squares is doing is just finding A to minimize this. This is literally where least squares come from. So this is called maximum likelihood rather than max a posteriori because we're ignoring the prior and only looking at the likelihood. Now, I'm going to explain to you a little bit here. I know there's some talks later on about intuition in data science, or maybe that was at Anthill. I can't keep track of exactly where everything is. I'm going to explain why you actually need that prior opinion if you want to get good results. Multicollinearity is a word that a lot of people know, and what it basically means is that your input data is highly correlated with itself. So, if we're looking at machines, we want to know the price of a machine. There's two pieces of input data that move together a lot. One of them is how many hours the machine has spent working. So that's literally the time the machine is digging a hole or moving concrete or something of that sort. The other is the age of the machine, which is how many years ago it was purchased. So except in rare cases where a machine was sitting in a barn for 2 months or for 2 years and not doing work, generally speaking, the number of hours and the age are basically the same. I mean, up to a constant. Hours is measured in hours, age is measured in years, but there's a clear linear relationship between them. This is a data set where least squares is not going to work well. So if there were no relationship between age and hours, and we looked at the likelihood, it would look like this. It would be just a perfect little spot at some location. So the x-axis is hours, the y-axis is age. What happens when your data is correlated is that the likelihood gets smeared out along a line. And that line is essentially the null space of the data. So essentially, since hours and age are correlated, we're saying one possibility, one choice of parameters that's plausible with the data is age is the only thing that matters. and hours don't matter at all. Another thing that's plausible is hours matter, age doesn't. The third thing that's plausible is age has a large negative effect, and hours has a slightly less large positive effect, and they magically cancel out. Like if you look at this, some of these parameters have different signs. So in some cases, we're saying an older machine is better and a newer machine is worse. But the hours worked cancel that out. So this is what comes if you just look at the data. So now, when you try to do ordinary least squares, you'll get a result. And if you use those same coefficients on data that's drawn from the exact same probability distribution, you're going to get really good results. It turns out this multicollinearity is not going to matter. But what happens is, if you have slightly out-of-sample data, if your model changes just a little bit between training and production, all of a sudden everything goes wrong. So what I've done here is I've generated similar data. So in the sample data, data is generated where x0 and x1 are 50-50 matched. In the out-of-sample data, they become slightly mismatched, 40-60 instead of 50-50. And also the value of y has changed a little bit from 2x0 plus 3x1 to 1.96x0 to 3.03. So really small model changes that you hope your model will be stable against. And then what happens is, with multicollinearity, the out-of-sample data, your predictions become horrible. They just don't work at all. Using Bayesian reasoning, we can essentially minimize this issue. So the company I'm advising, Heavy Equipment Research, I asked them, what matters more, age or hours? And he's like, oh, hours. That's where you get wear on tear. Who the fuck cares if it's a 3-year-old machine? As long as it's still in working order, it doesn't matter. But the thing is, hours are where you actually do damage to the machine. So what I did is, I took a prior. I took his opinion, and I turned it into math. And the math says age doesn't matter a lot, but hours matter quite a bit. So what I'm saying is, the coefficient on age should be close to 0. The coefficient on hours can be large. It can't be infinite, but it can be large. Then what I do is I actually compute a Bayesian posterior, which is the likelihood times the prior. And what happens here is, remember, we had this diagonal line. We multiply that by this horizontal line, and we essentially get the intersection. So now we have a pretty clear result that hours matter, age matters, but only a little bit. And so what we would want to do then is max a posteriori again. And we'll get results that are not quite as accurate on our test data as we get from ordinary least squares. But on the out-of-sample data, things work really well. Here's what's happening. Ordinary linear regression says, I don't care what, I'm going to fit the data as perfectly as possible. I don't care how plausible my results are. So if you have a bunch of numbers between like 0 and 5, ordinary least squares is happy to tell you, okay, yeah, we get the number 1 by saying 101 minus 100. It does add up to 1. But we're essentially saying there's this magic perfect cancellation that happens out there in the real world with real messy data. Bayesian says, that's just crazy. There's no way the real world is generated by 101 canceling 100. So we'll do something a little less accurate, but that seems more plausible. It's essentially putting your opinions above the data a little bit. But then what happens is, if you look at out-of-sample results, the frequentist is going to get a small tweak to the model, gets you crazy results from the frequentist ordinary least squares method, whereas the Bayesian model is still plausible. It may not be perfect, but it's in the realm of plausibility. It hasn't completely blown up. If we again do the same trick we used to derive least squares, what happens is the prior is an e to the minus gamma term. So again, we do some arithmetic, take the log of both sides, we get this penalized version of linear, we get essentially ordinary least squares with an extra term. And that term basically penalizes coefficients that are large. So it tries to fit the data without making the coefficients too big. And this is actually what ridge regression is. This is where ridge regression comes from. It's basically putting a prior on your data. Okay, I'm running a little slower than I'd like to be. So I'll just mention there's quite a few other choices depending on what you think the data looks like. A popular choice is L1 instead of L2, which basically leans you towards sets of coefficients that have a lot of zeros. So you'll still try to fit the data, but if you have a 0.01, you'll round that down to 0 because you think that's more likely. Most of the problems you run into from least squares are caused by this frequentist lack of an opinion. So I've got another example here that I'm going to sort of gloss over a little bit. The big idea here is when I was gambling on baseball, a lot of players have been in 50 games. I have a good estimate of how good they are. Some of them have only been in 2 games. I still need to place bets based on what's going to happen tonight because it's a new player, some hotshot, he's in the game. I can't just ignore him. So let's say Chris is the new player, and I've been in 1 game. What's essentially going to happen is if you just do ordinary least squares, the results of my last game, out of 1 game, I might have done really well. It's probably a fluke. If I did well in 1 game and then it was probably just luck the first time. And least squares will just say, that's not luck, that's truth. Another thing you can do is you just sort of round everyone close to the average. So this is, again, a prior that says most people are average until I have evidence otherwise. I'm going to gloss over this one a little bit in the interest of time. But basically what happens is as you get more games, you'll move further away from average towards whatever the true value is. So in cases where you have a lot of new data with very little points, just forming an opinion, most people are average until proven otherwise, is a great way to mitigate that issue and avoid the instability that otherwise comes. Outliers. One of my favorite interview questions is to ask about outliers. And here's the question, what the heck is an outlier? You get all sorts of answers like, it's a thing that doesn't seem to fit with the data, it's caused by errors, no one quite knows how to define it. The problem with outliers is that they're a miracle. So, for those unfamiliar, this is a photograph, this is a painting of Jesus walking on water. I think the odds of seeing a person walking on water as opposed to just falling in is very low. Now, if I actually see this in real life rather than a painting, I will just become a die-hard Christian right there. I've seen something wildly unlikely, but I saw it with my own eyes. I have to update my opinion on that basis. So, outliers are essentially the same idea. So here's the problem with outliers. I have a nice clean data set, and you see in the bottom right corner, there's that 1 extra data point that just doesn't fit. Now, ordinary least squares assumes your errors are a normal distribution. And as a result, they have to fit that data point. The net result, so you can see in this test data, the prediction just doesn't match reality at all. And the problem with this is that normal distribution is a really strong opinion. It's saying that point way there in the lower right corner is impossible. So when something impossible happens, you have to really change your view on the world. So it's a 4 sigma outlier, and the probability of it occurring is 10 to the minus 5. Whereas, so what happens is you radically change your worldview. You skew that line very far just to fit that 1 data point. So here's another possibility. Maybe my errors are not normally distributed. When you have a data set with a bunch of points that are just not that close to the line, maybe the Gaussian assumption is unreasonable. So here's a graph of a Gaussian versus an exponential decay and a polynomial decay. And as you can see, these are different choices on how rare I believe one of these distant events to be. And if you start to see a bunch of 4 sigma, 5 sigma events all the time, you know that it's just not a Gaussian. On the other hand, if we compute the probability of that distant 4 sigma event with an exponential distribution, it's not common, but it happens about 1% of the time, a little less. With the Cauchy distribution, it happens 7% of the time. So if we have a different opinion as to how our errors are distributed, we might update our inferences. So that was a data set with about 100 points, and one of them was kind of far out. It kind of agrees with exponential distribution. This is a very hand-wavy way to do it. There's more rigorous methods, but sort of a guesstimate that is hopefully plausible here. So all I had to do to use the fatter tails is I replaced my Gaussian with an exponential distribution like this. As a two-sided exponential distribution, not the normal one-sided exponential. So I literally just altered my log likelihood, and that happens to be just the vector norm in one dimension, and then we minimize it. So we have to use this, again, there are some tweaks necessary here. Nelder-Mead is a method that deals with the fact that absolute value x has a discontinuity. Minor computational optimizations. And so as you can see, the green line is the true line, and the yellow line, which matches it, I hope everyone can see the yellow line, just says, okay, yeah, one data point is far off, but all the other data points are on this line. At one data point, it fits our assumptions. It's perfectly plausible. I'm not going to change everything just because of that. It's not a miracle. It's just what you expect once in a while. So essentially, by tweaking this error distribution, you don't have to do anything special for outliers. Outliers are a real part of your data. And if you understand where they come from and what they look like, you can just build a model that fits them. This is Nassim Taleb, fairly famous figure. He is constantly pointing out to everyone in the world that you should not assume a normal distribution. He says that no one knows how to use fat tails. He exaggerates a little bit because that is his nature. But he raises a very good point that everyone assumes a Gaussian, everybody knows a Gaussian is false, and they keep doing it anyway and getting bad results. You should be aware that it's wrong and try to take it into account. I'm running a little short on time, so I'm going to skip ahead just slightly. Another thing that happens, discuss non-Gaussian data a little bit more. So in the real world, a lot of data is just not even highly centered. Here's one example. So I have a bad cricket data set that I don't fully trust, and I have a good baseball data set that I trust tremendously. So this data comes from baseball. This is the distribution of scores for the player Omar Infante. This is the distribution of scores for Chris Stewart. So if you notice, this is approximately exponentially distributed for each of these players. Mike Trout's really good, which means that he's more likely to get 30 or 40 points. These are fantasy points, by the way, not real points. This is for fantasy sports. Whereas Omar Infante, he can also get a 30, but it's less likely. Chris Stewart, probably not. He's not as good. What's varying here is the decay rate of this exponential distribution. The data is not centered anywhere. If you graph the data, most people score 0 points in any individual game. So this is not an exponential distribution. It's not a Gaussian. This is not any kind of a centered distribution. Here's another issue that you run into a lot, particularly in stock market data. So one of the assumptions of least squares is called homoscedasticity. What this means is that the variance stays the same regardless of the value of x. So if we're looking at stock prices, we have some predictive factor, and we're hoping to see kind of a line where that predictive factor goes up, the delta S goes up, and therefore when that predictive factor is high, you buy, when it's low, you sell. In the real world, a lot of data looks like this. When that predictive factor is low, things seem to go up a bit, and when that predictive factor gets very high, everything kind of blows up. Sometimes it goes very high, sometimes it goes very low. And moreover, the variance of your distribution changes with the input. The variation in y changes with x. And this is the real world behavior. And so one thing to really note is if you want to be gambling on the stock market, this is an area where you go all in. This is a pretty safe bet. Over here, this is 0. You don't want to gamble all your money out here. There's a good chance you're going to make money. There's also a really good chance you're going to lose everything. So you really want to understand this. It's really important to understand how this variance changes because that's where your risk lives. Even if it's a bet with a high expectation, the variance is so large that you should be afraid of it. So again, we're just going to do the same trick. Since we look at our data, we kind of formulate a hypothesis about it. And the hypothesis I'm going to form is that not only does the mean of my normal distribution change with x, so does the variance. And they change at different rates. I don't know what those rates are, but I'll try to find out. So if you plug this into the same formula, do all the same arithmetic, you basically get this similar Python code. It's just a slightly more complicated log likelihood. Do the same minimization. A couple of computational tricks I'm going to gloss over because running low on time. And essentially where similarly least squares just doesn't fit very well, the maximum likelihood fit with this modified model that takes into account where your data is coming from fits the data very nicely. Another really great thing about this method is you see the light gray lines at the top and the bottom. That is what's coming from, so we found A2x. What A2x represents is how the variance changes with x. So by doing this, not only do we get an estimate of the average, we're also getting an estimate of the variance, which actually helps us really avoid that danger zone. It helps us basically make bets when it's nice and safe and avoid the really dangerous cases, or at least reduce my exposure there. So basically, just by tweaking these parameters based on some understanding of the data and careful modeling, we can extend linear regression to a wide variety of cases where it seems like it shouldn't apply. And again, these are 3 examples where either I or someone I know has really made money off it. So I should also mention that none of this is limited to linear regression. If you have some other differentiable model, if you're a neural network person, this is also a great way to essentially figure out what your loss function should be, or to figure out what parameters you should be predicting. So essentially, if f of x were something other than linear, it could be your favorite neural network, favorite LSTM, whatever, you just wrap it in the appropriate loss function, which you derive by looking at your data and figuring out what you're trying to optimize. Do the same tricks, gradient descent, SGD, all that stuff is going to work for the most part, assuming you don't choose G too crazy. And you can do all the same stuff, but more accurately predict what you want just by understanding the problem bit. So I'm going to conclude here. Richard Feynman was a famous physicist, and he had what he called the Feynman problem-solving algorithm. Write down the problem, think really hard, and then write down the solution. It was very tongue-in-cheek. He was much smarter than most people, and most people couldn't actually do this. Key point I want everyone to take away from this talk is don't skip step 1. If you do everything I've done in this talk that solves a lot of real-world problems is literally just step 1. Write down the problem carefully, and then everything else follows. And I'm hoping some of you guys leave here and do the same thing. Do I have time for questions?
We have 5 minutes for questions.
Hello. Hi. Hi. I have 2 questions actually. First is that when you have a non-conjugate prior, right? Non-conjugate prior,
Sorry, please, I'm not hearing you very
When
well.
you have non-conjugate prior,
Okay.
and then how do you estimate the parameter? You still do this MCMC or any other trick?
Sorry, are you asking what to do about a...
So when you have non-conjugate prior, right? So
Okay.
prior and posterior are not in the same distribution.
Yeah.
And then you can still apply MCMC algorithm?
You can use MCMC if you... So if you want to understand the full variance of your estimates, you would need to use MCMC or something like it. I mean, MCMC is just a brutal first choice. It works well, but if you can optimize it, it'll be better. Or you could use max a posteriori if you just want one point estimate. It really depends on what your use case is.
Okay. Okay, and one more question is like, once you do this Bayesian linear regression, right? So, for example, in simple OLS, we verify a lot of assumptions.
Sorry, I'm having a little difficulty.
So, when we do this Bayesian linear regression, right? Hello?
Yeah.
Yeah, so once we finish this Bayesian linear regression.
Can anyone? Yeah.
Yeah, so once you do this Bayesian regression, right? So what are actually the, for example, in linear regression, simple OLS, we check a lot of...
I can't hear anything back here. Sorry. Can you translate? Okay. I'm sorry, I'm just having difficulty hearing. I think the acoustics are less than great. Okay.
Hi, my name is Amit. Thanks for the talk. In the initial at the start of the talk, you said that something does not work, right? A stock prediction that you were doing, it no longer works.
Correct.
So, what actually changed in the? Did you analyze why it didn't work anymore? What changed?
So essentially, what happened is, so when you were running a strategy like what I was running, you want volatility, which means the market goes crazy. And essentially what happened, I guess it's about 4 or 5 years ago now, the markets became boring and politics became interesting. So essentially all the volatility in the stock markets kind of vanished, and basically things only move once in big perfect movements when, like what happened yesterday, Facebook's earnings weren't great, and instead of going like this, they were just like, done. And that wasn't really something the model was built to take advantage of. Essentially what happened is there were a lot of guys just like me in the market running algorithms like this, and the markets became more efficient.
Any more questions? We have time for at least 2 more questions.
Any other questions from the audience? We also have Slido, so if you want to ask questions anonymously, you can do that. You can also upvote your questions. There's one from Slido here which I'd like to ask. Is it okay to use betas from penalized regression for attribution purposes?
Sorry, is it okay to use?
Beta from penalized regression for attribution purposes.
What do you mean for attribution?
The second part is, can I multiply beta times x value and say that that is the impact of x on y?
So that's more a question about causality versus correlation. So linear regression technically only finds you correlations. If you want to determine true causality, it would be better if you would really need to inject some controlled randomness into the situation. Like you would need to change one of these x1 at random in a way that you're certain does not change x2. On the flip side, you would need some kind of clear understanding of why x1 and beta 1 must be the causal factor and x2 is just correlated with it somehow. So causality is a much trickier thing to measure.
Okay, thank you, Chris. For people who are standing behind, we have a balcony upstairs. So if you don't have a seat,